I am a professor in physical geography at McGill University. My main area of research is in what we call biogeochemical cycles. I'm particularly interested in studying how carbon circulates around the world and its relationship to climate change. In the talk I give, I am talking about a particular storage of carbon that is unique to Canada, which is what I call the cold carbon storage. Vast landscapes of northern Canada are buried under several meters of peat, and there's so much carbon in this peat that it's actually globally significant in the climate change question. The reason why we're really interested in it is that that carbon has accumulated over the last 10,000 years since the last glaciation, and it's basically inert. It has nothing to do with the atmosphere. But if we have climate change in the north, or alternatively, as we are planning to do, develop the north through land use change, we would expect a portion of that carbon to go into the atmosphere. Everybody hears about land use change in the tropics. The tropics are sexy, there's lots of animals there, lots of organisms and bugs. We don't hear anybody talking about the cold carbon in northern Canada. But it is as large a carbon pool in the global carbon cycle as is the tropical rainforest.
Well, ladies and gentlemen, good evening and welcome to the fourth lecture in the series, the mini-science series, on climate and weather going to extremes. My name is Tim Moore, I'm the moderator this evening, and I think, as you can see today then, we have a contemporary issue in terms of climate change, and particularly in terms of the way in which we need to be able to control the way in which we manage carbon, particularly in northern environments. So with that applause, Nigel.
Thank you very much for the introduction, Tim. Okay, so I hope to talk to you tonight about a topic that I don't think many of you have actually probably thought much about. I hope to introduce you to a topic that will get you thinking about it and get you thinking about it in terms of why it's important as Canadians in particular to think about this problem of climate change and basically the carbon that is in northern cold ecosystems, and there's a reason why that carbon is there. I want to talk about our current problem to start with, and I use the term our current problem, not the problem, because it is our problem. We've generated this problem, and we will have to resolve this problem, and we will have to adapt to the problem of climate change. We are responsible for it. There's no one else that we can blame about this. It is us. The issue that we're faced with is that basically the Earth is warming. This is the temperature record from 1850 to the present time. It's the record that is reasonably good to use. There's three lines on there because there's three different international groups that compile this data and use a little bit different data sets to do it. But what you see is you basically see an increase of somewhere around about 0.8 degrees C to 1 degree C over the last 140 years or so. Relative to, the zero line here is relative to an average from 1990 to 2010. But it shows the temperature anomaly, and it goes up pretty steady from 1900 on. There is variability in it, and I'm sure in some of the other talks people explained about the variability. We're dealing with dynamic systems, the atmosphere and the ocean that are coupled together. If we want to do the attribution of why this temperature increase is happening in climate change, in the IPCC documents, the models give us the analysis where we look at this. And if you look at the very top bar graph, that is the observed warming. So that is the integrated warming from 1850 on, which is approximately 0.7 degrees C in this analysis. Actually, this goes from 1951, pardon me, to 2010. The greenhouse gases, the attribution of greenhouse gases to that forcing is you see that they would account for almost 1 degree C temperature increase. But at the same time, we're putting aerosols into the atmosphere, which actually block out a bit of the sunlight, so they actually decrease the temperature somewhat. So that offsets, so the actual temperature increase is less than just the greenhouse gases would do themselves. The range that you see at the bottom, on the bottom two graphs, are the range that come from natural forcing. So no matter which way you try to explain this, you cannot explain the temperature increase unless you use the greenhouse gases and the increase in greenhouse gases that have occurred. This is one of the most iconic graphs in geoscience. It's a graph that comes from Mauna Loa. It is measurements that started in April 1958 by Keeling. And it shows the secular increase in CO2 in the atmosphere of going from about 320 parts per million when they first started doing their measurements to now it's over 400 parts per million. Before the Industrial Revolution, it was at about 280 parts per million. The other reason why I show this graph is it shows a very, very interesting feature. You'll notice that the monthly data, which is the red line on here, goes up and down, up and down. And it was very interesting when they first started doing these measurements because they used an instrument that's called a gas chromatograph. And gas chromatographs are notorious for being sensitive to temperature. And if you're an analytical chemist and you see that kind of wave going up and down, you would assume that it's something that there's a temperature wave that's affecting the detector that you're measuring CO2 with. After tearing it apart, Keeling, after 2 years, convinced himself actually that they were seeing something real in the atmosphere. And this is the first time that we really understood the extent to which the biosphere affects the CO2 in the atmosphere. Those 6 part per million excursions that you see going over 12 months are, when it's dropping, are the northern forests taking up the carbon, the growth of the trees in the boreal forest, and then the rise up is the release of that carbon when the leaves fall off the trees and are decomposing over the winter and the next spring. So this motion up and down really indicated that the forests in the north had the potential to actually modify the CO2 in the atmosphere. And we finally got a little bit clued in at that point in time about looking at the biosphere also in the role that it plays in this issue that we have with CO2. So where is the CO2 that's in the atmosphere? Where did it come from? We've put into the atmosphere almost about 2,000 what are called gigatons of CO2 into the atmosphere. A gigaton is a very, very big number. It's 10 to the 15 grams. It really doesn't matter. It's a huge number. And since 1750, it's estimated that we've put about 2,000 gigatons into the atmosphere of CO2, or if you just want to think about the molecule of carbon, it's about 500 gigatons of carbon that we've put into the atmosphere. That has come from a number of different sources. On this graph, the gray area at the top shows you the cumulative emissions that have come from fossil fuels, industrial production, and cement. The production of cement. The yellow underneath it is carbon that's in the atmosphere that's resulted from us changing the ecosystems that are on the surface of the Earth. I'll explain this a little bit more later on, but when we take a forest and we cut a forest down and we make it into an agricultural system, that results in a net release of CO2 to the atmosphere because you've taken all the carbon that's in the trees, released it to the atmosphere, and you've replaced it generally with annual crops, which don't take up as much CO2, and release it back to the atmosphere in a much shorter cycle. Below the line is where that carbon is ending up. We're very fortunate that we have ecosystems that are taking carbon up on the Earth, and we have the ocean. About 50% of the CO2 that we put in the atmosphere ends up in other terrestrial ecosystems and the ocean, and only 50% remains in the atmosphere. If we did not have those sinks on Earth, we would be seeing much greater temperature changes than what we're observing at the present time. So if we did, there's a group that's called the Global Carbon Project that do the analysis every single year they go through this. This is their latest slide. The number for the synthesis for the decade going from 2004 to 2013. On your left-hand side are the two sources of carbon to the atmosphere. About 91% in that year, over those years, of the carbon that went into the atmosphere came from the burning of fossil fuels and cement, and about 10% came from land use changes. Where that carbon ended up, 44% of it ended up in the atmosphere, and that's the CO2 we see going up. And then the rest of it was roughly split between other forests that are growing back on land and the oceans. Now, you may have heard about this little meeting that happened in Paris just before Christmas. It was called COP21. COP stands for the Conference of Parties. Those are the countries that signed on to the original United Nations framework for climate change in Rio. And the COP meetings have been going on for years. There was a fairly big breakthrough in Paris where finally we've got most of the industrial countries, and in fact 195 nations, agreed to, one, that actually climate change was happening, and two, agreed that humans were the major source of the carbon to the atmosphere, which is a major breakthrough at the political level. They also agreed that they wanted to take measures to try and keep the temperature from increasing less than 2 degrees C by 2100. And preferably, they would like to keep it below a temperature increase of 1.5 degrees. Now, the reason why they picked those two numbers is because the climate models suggest to us that the wheels really start coming off the bus if we increase the temperature more than about 2 degrees C. It's where there's problems with ocean circulation. We start getting dramatic changes in ecosystem distribution on the Earth. We start seeing widespread permafrost melt. And so a lot of people are very concerned about those things. We see large-scale glacial melt. But this is a notional idea that 1.5 degrees C, 2 degrees C is where we get to dangerous climate change. Now, I'm sure you all read UN documents and all read Intergovernmental Panel Accords, climate accord documents. They're absolutely great. If you're suffering from insomnia, these are guaranteed to put you to sleep. If you look at the actual wording of the document buried in it, it actually tells us what is going to be required by 2030. Right now, we're emitting about 40 gigatons of CO2 to the atmosphere a year. If we continue on our current trajectory, by 2030, we should be emitting 55 gigatons. And what it means is that to get on this trajectory to have 2 degrees C increase, or limit to 2 degree increase, is that over the next 16 years, we have to reduce our emissions by 37%. Now, this graph is a kind of confusing graph. You just let your eyes go blurry. What it is, it's a bunch of different scenarios that are on here. We don't know the way the future is going to unfold. So what the climate modelers do is that they go to the economists and the people that talk about population dynamics and various different technologies, and they have a whole series of scenarios, and they put those scenarios in the climate models, and they run the simulations, and that gives us a set of lines that come out, which are the trajectories for the way the climate system may go. There are 4 main trajectories that they've done the collective examples over. One, and they generally relate to, they call the scenarios representative scenarios, climate projection scenarios. 8.5, 6, 4.5, and 2.6 are the labels that are on this, and that's roughly related to the CO2 in the atmosphere. The black line that you see on there are the historical emissions that we're on at the present time. And so the last estimate we have on there is 2014. You'll notice that that line is following the red line. That's not good. That red line is what is referred to as the worst case scenario or business as usual. And we are being successful at following business as usual in the sense that our emissions are still quite high. The gray line is a line that if we wanted to end up at temperature increases somewhere between 2 to 3.7 degrees C by 2100. The yellow line is if we wanted to be at 1.7 to 3.2. And the blue line is if we want a temperature increases somewhere between 0.9 and 2.3. The range of temperatures are because different models give you different answers that come out. So those lines tell us what we have to do from a perspective as a biogeochemist, it's what the climatologists are telling us that we need to follow as a trajectory for CO2 to obtain that objective of 2.3 degrees C. So I've put some numbers on here. For example, if we want to keep it at the low end of 2.C in RCP6, we would need to reduce our current rate of increase, by 50%. We'd have to cut it in half, our emissions of the rate that we're increasing, which would mean that we would stabilize out at about 35% higher emissions that we have in the present time on an annual basis. To get the yellow line, we need a full 50% reduction in CO2 emissions by 2100, and we'd have to follow that line. And to actually get down to the 0.9 to 2.3 degrees C range, we have to do 110% reduction in CO2 emissions. What does 110% mean? 110% means is that no fossil fuel emissions, no cement production emissions, and we have to figure out some technology that's going to take additional carbon out of the atmosphere. Right? So I do this to give you some perspective on what this 2-degree challenge is that's out there that the COP21 came up with. Okay, so this is where we will be in 2030 when the COP, they said that they wanted to have stabilization by. That's the amount that we need to reduce. That's the 37% reduction, 38% reduction that we need to have over the next 14 years to be able to hit this target. Okay, so what does that mean? These are the CO2 emissions and the rate of increase of CO2 emissions from fossil fuels in the black, and in the yellow are land use change. Both those have to come down, and they have to come down dramatically for us to obtain this 2 degrees C or less change. So it means that we need to work on fossil fuel emissions, and at the same time, we have to reduce the emissions that would come from land use change. And we have to do this at the same time when we're increasing approximately 4 billion people on Earth. We'll be up at about 11 billion people. We've got to increase food production. We've got to increase water use, or we're going to be increasing water use. All these challenges are ahead of us. This is what we tend to call a wicked problem to be able to solve this one. Okay, so I want to talk about the natural side. What can we do with that land use change? So if we take a natural forest, in Canada, for example, a typical forest up in the boreal forest region will be taking up carbon. That carbon will be going into the soils and be stored in the soils. Every once in a while, there'll be a forest fire that'll put some of the carbon back in the atmosphere, and then we'll have regrowth. So when that regrowth is going on, there'll be large uptake of CO2 out of the atmosphere, and that builds up these huge residual stores of carbon on the landscape. If we take that and interrupt the cycle by changing the land use, what we're doing is we're removing the primary constituents of those ecosystems that are taking the carbon up out of the atmosphere and replacing them with alternate plants, which is largely food plants for food production, which take up much less CO2 but also turn that CO2 over quickly. A typical boreal forest may have the same CO2 in it for 200, 300 years. An agricultural crop is done every single year that turns over very quickly. So it actually ends up being a large net release of CO2 to the atmosphere. So how is Canada doing in this picture? Our Prime Minister, the current Prime Minister, at least recognizes the problem and suggests that we might want to do something about it. This is actually a graph from the previous administration from Environment Canada that shows Canadian emission in megatons of CO2 per year. And the last number on there is 2014, where we were at 726. You'll notice that 2008 and 2010, there was a precipitous drop. I'm not an economist, but this indicates that recessions are good for CO2 in the atmosphere. If we went into a permanent recession, we might solve the problem that way, but I'm not sure that people would advocate that. If you look from 2010 on, however, and we project out to 2030, I've had to put the axis on the graph, that is where we will be at on our current trajectory. The target we need to be at, if we're going to meet our COP21, is that dot there, which would be about 460 megatons that we would have to release. So the question is, how do we get it down in that direction? We can look at where the emissions come from, and this is the distribution of emissions from Canada: oil and gas, transportation. We have a large country, sparse population. People do a lot of traveling. We have a cold country, so a lot goes into heating, building, electricity that we put in there. Agriculture is a big emitter, and the production of electricity in areas that they don't have hydroelectric power from coal-fired generating. You'll notice on this graph that there is no release of carbon, of CO2, to the atmosphere for land use change in Canada. Right now, the best estimates is that there is no net release of CO2 to the atmosphere for land use change. The reason for that is that Canada at the present time is not opening up a tremendous amount of new agricultural land. It's not converting forest to agricultural land. And we have quite advanced replanting practices for forestry areas that we're doing. So we tend to be fairly carbon neutral. We also have the advantage that large areas that were cleared when the Europeans first came to North America are actually regrowing in secondary forests. Most of the forests you go look at here in Quebec are actually secondary regrowth forests that you're looking at. The land was originally cleared, and that's now taking up CO2. So we tend to be carbon neutral on the land. This is a graph done by a fellow named Skye Houghton, who is at Woods Hole Ecosystem, who has tracked and done, probably the person that's worked the most on carbon tracking in the world for land use change. If you look at the lines on here, look at the United States. What you see is the United States in about the 1920s and on was actually a net sink for carbon on the land rather than a net release. And that actually makes sense if you think about it, because the Europeans cleared all the land in eastern U.S., and then when the Oklahoma areas and all those areas opened up for agriculture, they left the east, and it's basically regrown. So all the forests you see in the White Mountains and all those areas are regrowing forests that are taking a lot of carbon out of the atmosphere. Canada is the yellow line that you see, the bright yellow line. It's fairly small. It goes right along the bottom there, and we are in zero right now. Some other countries in the tropical regions are releasing an awful lot because there's a tremendous amount of land clearing that's happening in the tropical forests being replaced by agriculture and for purposes of cattle. Now, I put these two slides in because I get this question. When I did a talk about 4 months ago, somebody said, yeah, that's right. That is all really good, Nigel, but Canada is a really small player in the world. And this is the graph. If we look at the gross emissions of CO2 to the atmosphere in 2011, Canada, 2011, we've been pretty consistent from 1990 on, represents 1.6% of the total emissions of CO2 to the world, to the atmosphere. China has replaced the United States as being the largest single emitter at about 25%, and the United States is now at about 15% of all emissions if we add it up. Okay, so we're really a small contributor to this. But before you start feeling really good that Canada's a small contributor, let's look at the per capita numbers. Canada's number one on per capita emissions, right? So you take that number that we emit and you divide it by our population, which is 10% of the US, and now we don't look so good, right? In fact, this isn't a competition you want to be good at. We like to win at hockey. We like to win at curling. This is not what you want to win at, as in terms of per capita CO2 emissions. The other graph that you see on your right is the CO2 emissions per GDP in the economy. And what you see is we're right up there with the total greenhouse gas emissions per GDP and also the energy emissions associated to that GDP that we produce. So we do have a problem, and this means that Canada is actually one of the countries that has a lot of investment in that CO2 that's in the atmosphere. On a per capita basis, we're doing the best in the world. So now I want to talk to you about a unique Canadian problem, or northern problem. This is a map of the total carbon in ecosystems in the world. The darker the landscape, the more carbon that's in the ecosystems in the world. We tend to think that the tropical rainforests hold all the carbon, and they are fairly dark brown. But if you look in northern Canada, northern Europe, and Russia, you see some really chocolate brown colors up there. What that's indicating is that if you go stand on a landscape, every square meter that you're looking at beneath you in those areas that are the dark brown, there is something like 200 kilograms of carbon underneath your feet. If you go stand in a tropical rainforest, one of the really thick tropical rainforests, you might have 20 to 30 kilograms of carbon surrounding you and in the ground. So these sites are 10 times more concentrated, the carbon in them, than they are in the tropical rainforests. I put the box around here in case some of you didn't know where Canada was. But this is a diagram that I don't expect you to read, but it's talking about all the different pools and storages of carbon that exist in the global carbon system. If I put the numbers on for Canada that are in red, what you see is that Canada has about 4 to 5% of all living biomass, that's trees, within our boundaries. We have about 15% of all world's soil carbon, and we have about 35% of all the world's carbon that's stored in frozen soils in permafrost. So we have a very large bank account of terrestrial ecosystem carbon compared to a lot of other places in the world. This is a map of where that carbon is. Where it's red, there are very high carbon concentrations. Most of Canada is red. The boreal forest region, large extents of the boreal forest region have huge amounts of carbon in them. Why do they have huge amounts of carbon in them? Partly the boreal forest takes up a lot of carbon, has a lot in the soils, but Canada has a huge number and huge coverage of peatland ecosystems, bogs and fens. This is a map of the peatland distributions in Canada. And this is a map of the carbon concentration in Canada. And it all follows that band that goes through the boreal forest zone where Canada has a huge amount of carbon. Why is this the case, and what's the fundamental difference? If you look at a tropical forest, we would go down and look at a tropical forest, all the carbon is stored in living trees. You cut the trees down, you eliminate the carbon, and you also eliminate the uptake of carbon. But if you replanted that and it started growing again, you could replace that carbon fairly quickly. Quickly, I mean a couple hundred years. If we go to the boreal forest, we would find about 50% of the carbon is in living biomass above the ground, and about 50% of it is stored in the soils below the ground. The reason is they're cold, decomposition is not as quick, it builds up over time, so you have large organic layers sitting on top of the mineral soils. But if we go to peatland ecosystems, the living biomass on the top of peatland ecosystems is tiny. Tiny, tiny amount. But the amount of carbon that is accumulated over thousands of years since the glaciers have left is a huge amount of carbon. So we're dealing with a system where there's a lot of dead organic material. The reason why I stress this is that if you play with dead organic material, you have no mechanism to replace it again because the production in those ecosystems is extremely low. The reason why all that carbon's there is it's accumulated over 10,000 years or 8,000 years. What are peatlands? Well, if you go to northern Canada, these are systems that we've worked on, very large, extensive peatland areas. These pictures, some of them are from the Hudson's Bay lowlands. And the one that you see just up on the left-hand corner there is Mer Bleu, that's just south or east of Ottawa, that we've worked on. They produce massive landscapes of this mat of carbon sitting on top of the surface, which is dead organic plant material. It accumulates over years. The top layer of peatlands for about the top 20 to 30 centimeters is aerated soil. The water table then is at that level, and below that is anaerobic conditions for 4 or 5 meters. So you've got this huge carbon that's joined up. This is not, the second picture is not in Canada, it's actually in Ireland. It's a bog cut that's in Ireland. But the point is that the water table's high in these systems and the plants produce certain chemical compounds that actually inhibit decomposition. So that carbon's locked up and away from the atmosphere. This is not a picture of my former chair. I just want to point this out. But it does demonstrate how well the carbon is preserved in these ecosystems. This is Tolman Man that you're looking at. He was buried about 2,000 years ago. He has effectively been tanned the same way that a tannery tans leather. It's because of the phenolic compounds that are coming out of the plants and the anaerobic conditions. That gives you an indication of how well organic compounds are preserved in these ecosystems. If you modify those ecosystems where you change the water table then and make them drier, you would expect that carbon to start coming back out. So carbon goes in through photosynthesis, carbon comes back out by plant respiration. Most of it is buried in these ecosystems that builds it up, and the anaerobic decomposition also supports methane going to the atmosphere. So these ecosystems are globally significant for CO2 and globally significant for methane. If we look at climate change and the maps of climate change, these are the maps for Canada for climate change, on various different climate scenarios, you go across spring, summer, autumn, and winter, and you're showing the dates on the top of there for 2050 and 2080 for two different types of scenarios. B1 are the top two graphs. BA2 are the bottom two graphs. We're on the A2 trajectory right now for climate change. And if you look out, they're estimating temperature changes of 8 degrees to 10 degrees in the summer and through the winters in these areas that have these huge organic deposits in them. What might happen? This is some research a graduate student and I did. The dashed line that you see on each one of these graphs is the current rate of carbon uptake in these ecosystems. The bar graphs that are on there are simulations that we've done with an ecosystem model about what we think will happen to CO2 in the future. On the diagram that's on the left side is for a bog, mer bleu, and you see that all the lines, the bar graphs, are below the dashed line. What that means, but they're still positive, what that means is that they will remain carbon sinks, but at a lower rate, which means a slight carbon contribution to the atmosphere. The other line on the right-hand side is for a fen, which is a much wetter type of ecosystem. And in that, our scenarios in that case, we find half of the climate scenarios of the future change those ecosystems from being a carbon sink to being actually a fairly large carbon source to the atmosphere. So in Canada, 67% of Canadian peatlands are bogs, and about 32% are fens. Much of northern Canada's peatlands have permafrost, or many in them, about a third of them have permafrost in them. These are landscapes that are collapsing now. On the right-hand side is Kejuarapik in northern Quebec, where we're working, and in northern Sweden, Abisko, where we have some of our other sites. And these are large collapse scars, and what happens is when the ecosystem collapses, it goes from being a very dry type of bog, which is conserving a lot of carbon, to now being very, very wet, forming ponds on the surface, and the vegetation changes from being moss to being the really green plant you see on there, which is a sedge, which is very good at contributing methane to the atmosphere. So a transect across the site that we worked on in Kejuarapik, we have the frozen permafrost peatland on the left, where the CO2 uptake was reasonable. It's about the same as what we're measuring here at Mer Bleu near Ottawa. And there was virtually no CO2 coming out of these sites. It was too dry. Then beside it, you see the ecosystem that collapsed and the vegetation has changed. The CO2 uptake actually increases in those sites, so we're taking up more carbon. But now, because the plants have replaced it, the methane emissions are really large coming off these sites. And then if you go over to the thawed lake, the thermal karst ponds, the CO2 is now going out. It's not being taken up, so it's now releasing CO2 to the atmosphere and releasing methane to the atmosphere. This seems to be a widespread phenomenon that's happening throughout the north with permafrost melt. This is a diagram that came out in the Science magazine about 2 or 3 years ago. I'll try and situate you so you can, so if you go across the horizontal axis, those are years going from 2000 to 2012. On the vertical axis, if you look over on the right-hand side, it's easy to reference yourself. We go from 90 south, 30 degrees south, the tropic of Cancer, the equator, the Tropic of Cancer, 30 degrees north, 90 degrees north. The hot colors, green through to red, are where there's a methane increase. The hotter the color, the larger the increase in methane concentrations in the atmosphere. What you see is you see in the northern regions, you see fairly large increases in methane that are happening. Over the last 4 or 5 years, we've seen increases about 20 parts per billion of methane that's in the atmosphere. The station that's in northern Canada, the Pearl Atmospheric Chemistry Station, has measured the isotopes on that methane. We know it's biogenic methane, which means that it's methane that's coming from biological processes on the surface, and we know it's modern methane because the C14 in it is present-day carbon that's coming out. So we rule out that it's not sources from flaring from natural gas sites. It is probably from landscape sources of methane. This is actually a very scary proposition. And when I started looking at this, if you turn this on its side, it looks very close to Munch's scream, right? So that kind of is something we need to maybe worry about. Canada's north is not well developed. Any of you that have gone north in Canada, I had a Korean student that came here from the capital of Seoul in Korea, and he worked on northern reservoirs up in Hydro-Quebec, and he took his first flight up. He came back, and he sat himself down in my office. He says, "Professor Roulet, I have to tell you something." I said, "What's that?" He said, I flew up to the East Main Reservoir. I said, I know that, Kim. I flew you there. I mean, I paid for you to go. He says, no, but you don't understand. We flew, and then 20 minutes north of Montreal, there was nothing. All it was trees. And then we flew, and we flew, and we flew, and it was just trees, lakes, wetlands, trees, lakes, wetlands. I mean, Canadians take this for granted, right? But the rest of the world isn't like this. It isn't this vast area that has been touched, but is largely untouched as far as ecosystems and carbon's concerned. This is a road map on the bottom here, and there are no roads. Basically, they're going north. The other map on the left-hand side is the population density in Canada. We all live within 100 kilometers of the U.S. border, right? North of that, there's very few people that live there. So we've got a largely undeveloped area where all this land-based carbon is. We also have an aspiration that this is the next frontier for Canada's economy. The Plan Nord, the Ontario Far North Act, every province is looking to the north for minerals, hydroelectric power, the next development phase to go on these types of things. The world does need these resources to a certain extent, and if we're going to continue to consume, then the north would be developed. And the challenge would be, what do you do about this carbon when you develop in the north? I've put two maps up here. The one on the right comes from, or left, pardon me. Yeah, left comes from the Ontario Far North Act. Right now, the hot area there is the Ring of Fire. This is where Kathleen Wynne and Harper were fighting over who's going to build the railroad road to go in there. On the right-hand side is the Far North, or is the Plan Nord map of the areas for potential development for hydroelectric power, for minerals in those areas. Transportation corridors are going to have to go in. Power corridors are going to have to go in. I think you know the people that are on the left. I think you probably know most of the people that are in these pictures. The ones that are on the left, this is when Couillard and Wynne announced their desire to have a cap-and-trade system to be able to reduce greenhouse gas emissions. On March 3rd, 2016, this is in Vancouver, with our new Prime Minister leading the premiers of the provinces, when they had their pre-meeting for a meeting that's coming up this summer on greenhouse gases. And on March 10th, this is Obama and Trudeau on the lawn. It is where they talked about the Chicago Blackhawks winning the Stanley Cup, but they also talked about greenhouse gases, and importantly, they talked about methane. Methane is low-hanging fruit. We produce 2/3 of the methane that's in the atmosphere, and there's a lot of things that we could do to reduce those emissions fairly quickly. And so it may be low-hanging fruit for us to make advance on the CO2, but the methane is one of the problems that we have with ecosystems in the north. So how is Canada going to do this? How are we going to reduce? We've got to get down from that current trajectory down to COP21, and then we've got to keep going on that trajectory if we're going to make this too. There's only two ways to do this, is reduce fossil fuel emissions from cement production and the burning of fossil fuels, and also making sure that land that we develop in the north, we protect those high density carbon deposits and don't translate it into the atmosphere. There's really no excuse for us not knowing about this and not being able to forecast that this is going to happen, because we've observed it happening in the tropical rainforest and we observed it happening in the temperate forests. In fact, much of the carbon that's in the atmosphere from land use change right now is temperate forest carbon from when we and our predecessors cleared the land and translated that into agricultural systems. So we know that this is going to happen if we develop that land and we don't pay attention to the carbon. Just to give you one example of the scale of this, this is a carbon density map taken from the Swedish Bolin Research Center. I've located Quebec on here. If you do a rough calculation, Quebec in the Plan Nord area alone, I'm not considering anything south of 51 degrees north, has 20 to 30 gigatons of carbon in the soils, or that's equivalent to 70 to 100 gigatons of CO2. Now I know that I'm sure all of you use these mass terms all the time. That is equivalent to 850 years of Quebec's 2013 emissions of CO2. That's what's stored in those soils. If we were to convert 0.1% of that land a year, we would negate, and we reduced our emissions from fossil fuels to zero, we would negate the reductions that we've done in the fossil fuels in the conversion of these landscapes. So we've got to figure out how to keep that carbon there if we're going to develop that region. So in summary, we have a problem. We have committed to reduce emissions. We've said we're going to do this. Right now, Canada's CO2 is largely from fossil fuels and from land use activities, agricultural, those various different things on the land. But right now, we don't have a large source from land conversion from one land use to another. But Canada wants to develop the north. The north holds globally significant stores of carbon. What does the next 50 years have in store for us in terms of how we approach this particular problem? To me, this is the elephant in the room for Canada in the sense to think about this. And there are three questions I think we need to think about seriously. What moral obligation does Canada have for carbon stewardship for the deposits that are on the land? Okay, so I've told you those deposits are there. If you don't believe me, you can go up and dig the soil pits if you want and measure it yourself. I'm sure my numbers are in error by 25%, 30%, maybe even 50%. It doesn't matter. It just means it's a little bit more important or a little less important, but it's still globally significant. So do we have a moral obligation because we know it's there now and we know that we've got this problem and we know land use converts carbon into the atmosphere? What role should carbon management play in northern development decisions? In the sense that we no longer have the excuse to say we can use the atmosphere as a trash bin. We can just throw it in the atmosphere, it's going to disappear. We know that's not the case. And if we do decide to develop in the north, what mechanisms should Canada use to ensure carbon sustainability in developing the north? Our governments have told us that we want to have sustainable management in the development of the north. So I leave you with those three questions to think about and hopefully have convinced you. You may not believe the argument that I've presented to you, but I hope you're now going to think about this argument as being a little bit different. It's just not fossil fuels. We've got to protect what's on the land also. And I thank you.
Thank you, Nigel. So we're now ready to receive your questions. So you dealt with politicians, you dealt with the Couillard government in Quebec, but particularly you dealt with Kathleen Wynne in Ontario. I mean, do you find the politicians receptive to the ideas that scientists put forward, or is there some twist that you think is really important on getting these ideas accepted?
I think a year ago in March, I was asked, along with 3 other scientists, to if we would have a half-hour meeting with Kathleen Wynne to talk about the issues of land and carbon that was in the North. I was on a panel, a scientific panel for the Ontario Far North Act, and I think that's why she asked me to come down and talk to her. And that meeting ended up being an hour and a half, not just an hour, not just half an hour, but kept being extended on. And I was very impressed with the discussions that went on. I mean, I did not have to convince her at all about the importance of the carbon on the land. It turns out that she's a canoeist and that she has canoed the Attawapiskat River, and she saw all these peatlands. She traversed it. She spent 20 days or 10 days, I think, crossing the Hudson's Bay lowlands, and the person that led them on the trip was actually one of the environmentalists with CPAWS, so explained to them all about the ecosystems that were going on. And when I was sitting there talking to her about it, she said, you know, we've got to think about this in new ways. So one of the things that she's saying is that we're looking at, if we do develop the Ring of Fire, we've got to get the ore out. It's not, there is a mine that we actually work out of in the Attawapiskat area, which is a diamond mine, and they fly the ore out, the diamonds. It's just a handful of diamonds they take out a day, so they don't need a railroad to take it in and out. But if you're doing things like chromite, nickel, those types of things that the Ring of Fire has, you have to bring them out by a railway or by a road. And she said, when we were talking about this, I pointed out to her that the shortest route to do that is straight across the Hudson's Bay lowlands. This is the third largest peatland in the world, 240,000 square kilometers. It probably holds a third of Canada's carbon in it. And she knew that. And she said, well, what's the most important thing we've got to do? And I said, well, the most important thing you do is do not disrupt the way the water flows across that landscape, or you will destroy those wetlands. She said, what about an elevated railway? I said, what do you mean? She said, well, the Florida Everglades. If you go down to the Florida and the Keys, the roads are all elevated there. She said, why don't we build bridges that go completely across? So you put in these pylons. And I had been thinking about that you would put in the typical gravel railway bed that you would put in, and you'd put culverts, and I was trying to figure out how you could possibly put in enough culverts to be able to do that. So I'm convinced that she is at least thinking about these types of things. Now, she's a politician, and I think the truth will come out when you have to start making those tough choices about the economic interests that are driving these types of things. But if you go to, so one of the things she said, what would you suggest? I'm a great fan of putting a price on carbon. I think you've got to put a price on carbon. I don't care whether you do it by cap and trade or carbon tax. If the only thing that putting a tax on it does makes people think about carbon, that's good. I mean, people can argue about where the revenues go. I would put it solely into new technologies for reducing emissions if you did those types of things. But we've got to get people thinking about that. And the other thing that I think you need to do in Quebec and in Canada is that the environmental assessment acts that we use need to have in them the integrity of ecosystems and also need to have full carbon accounting in them when a proponent wants to do a project. So that it forces them to think about the environmental costs of the diminishing of services that natural ecosystems do for us. And she was on a similar page when I mentioned that. I mentioned that to her. The Couillard government, David is their environment minister, and we had similar conversations. So I used to work with the federal government. I hope to work with the federal government in the future, but the last 10 years have been kind of bleak up in Ottawa for those kinds of discussions. So I have some hope in the provinces.
Okay, so I have a series of questions, Nigel. One is obviously people can relate to burning of fossil fuels. Could you explain why cement plays an important role in the carbon dioxide budget of the atmosphere?
Yeah, sure. To actually make cement, you're making it out of rocks that contain carbonate. They're carbonate-based rocks. So that when you are making cement, you have to liberate a certain amount of CO2 out that's actually in the rocks in the killing process for making cement. So they're a fairly high emitter of CO2, though because they're done in large plants, they're putting in CO2 scrubbers to reduce the emissions. I don't know the numbers. When I was on the IPCC in 2007, about 6% of the total emissions of CO2 to the atmosphere were from cement production. So it's basically a carbonate chemical cycle for making cement.
So we've talked about these northern peatlands and the importance of anaerobic conditions. Can you explain a bit about what anaerobism means and how it's important in explaining the patterns we see in the north?
Sure. How many people here drink wine?
Anybody not drink wine?
Is there anybody that doesn't drink wine or beer? Okay, so you actually know all about anaerobic decomposition. It's fermentation is basically what goes on. It's the conversion of carbohydrates in the absence of oxygen. The normal process for respiration is that oxygen is what we call an electron donor for the processes of decomposing material. Once you put water in a soil, it becomes very difficult to get oxygen into the soils. If you've got a lot of carbon in the soils, it will use up all the oxygen fairly quickly. So now it means that you don't have any oxygen available. And we now go down that part of chemistry that you all hated when you took it called redox chemistry. We now go down what's called a redox ladder. And when soils become very anaerobic, the last decomposition process is essentially an acetate fermentation of organic material. And the byproduct that comes out of that is methane. That's the byproduct, the waste, or not the waste, but it's the fuel that comes out of it. It's microbes that are seeking carbon for their metabolism. That is what's doing it. So that's anaerobic decomposition.
So that slows down the rate at which carbon decomposes, but it also produces methane.
Right.
So can you explain a bit about why methane is such an important part of this process?
Okay. So methane, there's 3 greenhouse gases that are really important that are what we call biological or biogenic greenhouse gases. CO2 I've talked a lot about. Methane is the second most important greenhouse gas in the atmosphere, and then the other one is nitrous oxide, N2O. The carbon, so those gases are together, and peatlands give you, or wetlands give you what we call the two-body problem. They're good at taking CO2 out of the atmosphere and storing it in organic soils. And the reason why they store it is because they're wet, so it's incomplete decomposition. But the decomposition produces this methane. Methane on a molecule by molecule basis is a much more efficient greenhouse gas than CO2 is. It's 25 to 30 times more efficient than CO2 is at absorbing long-wave radiation. So if you get a lot of methane in the atmosphere, or even a little bit of methane in the atmosphere compared to a lot of CO2, the methane will do as much as the CO2 does in the atmosphere. The good thing about methane compared to CO2 is that methane has a chemistry, though. If you remember that game that we played, well, I'm actually looking at the age of the room. I'm sure most of you remember the game called Pac-Man. There's a radical that's in the atmosphere called the OH radical that actually cleanses the atmosphere and takes methane out of the atmosphere. And so methane has about a lifetime of about 12 years in the atmosphere. So that's another reason why it's low-hanging fruit. If we really stopped reducing methane, we would start seeing very positive results in 50 to 60, 70, 80 years. We would start doing that. With CO2, the problem with CO2 is you can really start reducing emissions now, and it's going to be your great-great-great-great-grandchildren that are going to start benefiting from those emission reductions because there's so much CO2 slowly circulating around the system.
So how can we reduce methane then? Is there a magical way of doing this, either microbially, or is there some sort of great Pac-Man geoengineering we can put into the atmosphere?
Well, no, not in the atmosphere. There's not. So I'm not a big fan of trying to geoengineer the atmosphere. But there are a lot of sources if you look at methane. So the first thing is that methane is released a lot from the processes of extraction of fossil fuels, both oil, coal and natural gas itself. We could capture that a lot better than we do now. The technologies are available now to reduce fugitive gases from pipelines and things like this. So, for example, when the Soviet Union was the Soviet Union, they used to lose a huge amount of the natural gas that was coming out of their natural gas fields as it came across down to the south. When the economy opened up, in fact, believe it was a number of Canadian companies went in and rebuilt the pipelines. The amount of fugitive gas decreased immensely. You don't want fugitive gas because you want it to go to market because you can sell it. Large source of methane is through agricultural ruminants, cattle. You could change it by doing the feed properly, well, feed not necessarily properly, but you could construct feeding regimes for cattle that would be much better, that would reduce, say for sheep, that would reduce the methane emissions that come out from them. It's because they have a foregut that they break down the cellulose in the foregut, and that produces the methane. Rice paddies, which are basically artificial wetlands, are large emitters of methane. China's been doing a huge amount of research on using different cultivars and different ways of doing it. So the numbers that we saw when we were at the IPCC is that we thought there actually could be 40% reduction in methane emissions without a huge amount of technological interventions, just by managing things a little bit better.
Thank you very much for coming tonight. And